rather for scientists and PhD students. And some 5 years ago, in 2015, he wrote this very good book, which is really meant for students. Many proofs are shortened or omitted and referred to this older book. And you can also find, which is your first suggestions for home preparation, to read very first chapter in the introductory chapter. After this, you have a lot of examples and exercises. And then also at the end of the book, you have many appendices. And one of these appendices is appendix number, I guess, A, or not number, but called A. And there are a lot of practically motivated systems, examples, which can you read in detail. There are many also ideas of methods which will be investigated or presented next in this course. So let's start with exposition. So you can see this is the basic model we will use. So we have n state variables, and they form ordinary differential equations. So x1 up to xn are state variables. Then we have some input variables, u1 up to um. All these quantities are scalars, and x1 dot, x2 dot, and so on denotes full-time derivative of this state with respect to time. So we are looking for time functions such that if you substitute to the left side and differentiate this time function with respect to time, and then you substitute to the right-hand side, then you will obtain identity. Of course, before you need to fix also input functions, because they are free and you can somehow affect behavior of the states, and that's why it is called controlled system. So here you can see all explanations. These presentations are already available in Moodle, so you can use them. So I will scroll by myself here only. So if you need to consult something, you can certainly look in Moodle later or now if you already downloaded. So if you, for instance, don't hear me very well or something is unclear, so please react immediately. So then, as in case of linear systems, we also are interested in some output relation. So output relation is already a static relation, is just function of state and input and possibly time. And the idea is that usually in practice, state, so then we can write everything here compactly in this way. I can repeat here these x, u, and y are compact vectors composed from those scalars. So this is much more nicer and compact description. And idea is that in all practical applications or situations, usually x is much of larger dimension than y. And the reason is that number of state variables you need is simply given by modeling, by situation, because you need as many equations, differential equations, as all aspects, let's say, of reality are present. So you need more and more of them, and many of them are just here because you need to have some form of equation where on the left-hand side and on the right-hand side you have the same number of states, while in reality you are interested only on some of them, yeah, so these output-wise. But if you would like to use only outputs, then you wouldn't be able to write down these equations, because you would need more and more variables. Typically, you may be interested only in some position of some object in usual Cartesian space, and you want to study its movement. But even if you are only interested in position, you still need velocity, acceleration, and so on in order to write down a model using Newton's laws. So even if you are not interested in velocity, then you still need to consider velocity, which is intuitively clear. So this system is terminologically sometimes called also dynamical systems or force dynamical systems, or many other terms you can find. So before we start to be interested in control, then we have to understand behavior of uncontrolled systems, because basically if you look here, so control of the system consists that you choose here some time function, then you may somehow assume that you can solve and see what solution you have, and then you may only think about how to choose input u in order to affect in desired way x and y. So it's good to understand what is happening with the system where already you have fixed behavior of the right-hand side. So this is the so-called unforced state equation. In general, it is just x dot is equal f t x. T stands for time. And clearly, you can obtain it either from the original control system in such a way that, for instance, you use some time function for your input. So then you will obtain this kind of behavior. Or you can use function of the state, then we speak about feedback. Or you can use in combination of t of x. So formally, mathematically, it's clear that when you substitute here for u time function, then you obtained kind of this unforced equation. When you substitute this, you again obtain some kind of function like this, and so on. Usually terminology, like in linear systems, is that when we substitute just time function, it's open loop control. Then if you substitute function of state, that it is feedback control or closed loop control, state feedback control, whatever you want in terminology. And also this is interesting, sometimes it is useful, it is the so-called time varying feedback. In general, of course, in earlier times of automatic control, this was feedback was most preferable, because it is assumed that the state is also something we can well measure or at least estimate. Then we are really not deciding according current time, but measuring really state of the system, and then deciding what to do to improve behavior of the system, and so on. But I think these days this time varying feedback may be also practically realizable, because you already can measure time also very precisely, and so of course this is the best option, classical state feedback, because you don't need to measure time and you measure only your state, and you are somehow not interested in real time. So example, are linear systems. What I show here is time-varying linear systems, so matrices A, B, C, D of some proper dimensions. I will not detailize. You can easily decide for yourself that A is n by n matrix and B is perhaps n by m and so on. And in general, they may depend on time, but the majority of good linear theory is known only for time invariant system when coefficients of these matrices are constant. Otherwise, when there is complicated behavior with respect to time, then it is also a very complex problem to study. Okay, so first we need to understand how this unforced dynamical system is behaving. And we would like to first of all study existence of the solution. So idea here is that when, for instance, we start with some controlled system and we decide, for instance, use open loop control or feedback control, then we arrive to the systems, and we would like to know if the model is as good that at least it has some reasonable properties, like then if we know initial state of the system, then we can compute how the system will be behaving in the future. Then we may decide if our control is good or not. But if the system doesn't have even these good basic properties, then probably we may conclude that it is not a good model. So for instance, if we have mathematical model of some real situation we want to control, and we discover that for some states we may have not, first it may happen that there is no solution, then it may happen that there is solution, but there are more than one solution starting from the same state. So because we would like to use these equations to predict our future and then to decide what to do. So how we can predict future if our model is providing either no future at all or several future scenarios. So we need to have this, what is called deterministic system. So we want to know that if we know current state, then the future can be for at least some time computed. And of course, the third ideal property as the future, which can be predicted, is infinite. So we can predict for all times in the future. But many nonlinear systems, they happen that they can be solved only on some limited time interval. Then they may have some sudden escape of solution to infinity, for instance. So these are three basic properties which, you know, for linear systems are so automatically valid that nobody even thinks about systems where this is not true. So for linear systems, always you know current state, you know input, some reasonable input. Of course, if you use some wild input trajectory or input signal, then of course strange things can happen. But if you use some reasonable input, then you know that you can determine future behavior uniquely for all times. So here we would like to start with some mathematical theory, how to study these basic properties when we have non-linear ordinary differential equations. So again, you can see here we will study this non-linear differential equation, and we will consider the so-called domain. Domain is open connected set by definition, which is subset of the whole state space Rn, and then we will consider some interval J, subset of real numbers, which will stand for some time range where we are studying the systems, and this calligraphic D stands for some range of states which is reasonable for us. And then we will ask two basic properties for the right-hand side. First, that it is piecewise continuous in T, right-hand side, f of t. And secondly, it is the so-called Lipschitz in X. So more specifically, we can decode these two properties. Number one, this simply means that if we consider some fixed state in this domain where we consider our system, and X is fixed, so this is converted simply into function of time, mapping time to Rn. And then we just ask that it is continuous at all points from considered time range, J, except possibly finite number of finite jump discontinuities. So piecewise continuous bounded function. Continuity of a function from R to Rn, you probably should know very well from many mathematical courses and others. I will not repeat what mean continuity of n-dimensional mapping or function. So motivation for such a minimum requirement is that, of course, we would like to consider input signals, for instance, gamma t, such that input signal will be some continuous functions, but possibly with some jumps. For instance, some piecewise constant function with some step changes at some time moments, which is quite common in control. And you know that for linear system, for instance, one of the basic characteristics is response to step function and so on. So we want to consider inputs which may be discontinuous, and of course one can find in mathematical literature even more sophisticated definitions of solutions, when we can even relax and consider even worse continuity conditions, but it's clear that for practical purposes in control, simply functions that are piecewise continuous are more than enough. And they are also reasonable because jumps may always occur. So the property number 2 is now property where we want to study how right-hand side ftx depends on x, on vector x. So to do so, we first need to give some definition, which we also may already know. It is definition of ball-like neighborhood of some given state x0 from Rn. Here you may correct, I will correct it later. Here should be Rn, of course, x0 is from this n-dimensional space like here. And intuitively it is clear the ball-like neighborhood is simply inner part of the ball with center at x0 and radius r for some r greater than 0. This is notation, and here is simply definition. You can see that all points from Rn which are closer to x0 than R. So which is intuitively like ball in three-dimensional space. In n-dimensional space, of course, you cannot imagine it. This is the so-called norm, and we decided to take the usual Euclidean norm, which is defined like this, or which is equal to this. So either square root from transposed row vector x and times column vector x. We consider all these vectors automatically to be column vectors, and if we want to consider row vector, then we put here the sign of transposition. So either this, or if you multiply this together, right, row vector and column vector, you will see that it is actually a sum of squares and then square root. So this is neighborhood, and now we can already give more precise definition of this property. So ftx is called local Lipschitz at x0 if there exists some real number, positive real number, R, and some constant, positive constant L, such that for all time moments from our time range we are interested in, and now for any couple of points, x and x bar, which belongs to ball-like neighborhood of x0, holds this simple property. So you take right-hand side and evaluate at any point t and some point x, and then you evaluate at the same point t and some other points x, and both these points are in this ball-like neighborhood of our initial state. And then these are two column vectors of the right-hand side. We subtract each from other, compute the norm, and then we ask that difference and norm of this difference is less or equal than difference between norm of arguments of x and x bar times this constant L. So this property is then called locally Lipschitz on domain D. So more precisely, ftx is then called locally Lipschitz of domain D. So, okay, f of t is called locally Lipschitz at x0 if this is valid only in some ball-like neighborhood. So maybe R is a very small number, and this hold only in this small neighborhood. But if then this hold on the whole domain, then we ask that at every point we would have this property. So we take domain, we take arbitrary point in the domain, and for this arbitrary point x0 in the domain, we find their own small ball-like neighborhood and its own constant L, and then we can have this property for all points from this small neighborhood. So this is locally Lipschitz on the whole domain. So then much more interesting property is when it is called Lipschitz on some set V. And this means that we have not only local Lipschitz property on this set W, but also this constant L can be taken unique for all points from whole V. Because here, locally Lipschitz means that at every point x0, this constant L may be different, yeah? But here, constant L would be the same for all points from whole set. And of course, the most ideal property is global Lipschitz, which means Lipschitz on Rn. So if W is whole Rn, then of course we will call it global Lipschitz, and it's the best situation we can have. So here it's important to understand that Lipschitz on domain is something completely different than local Lipschitz on domain. Local Lipschitz mean that at each point you may have own constant L, while Lipschitz on domain there is unique constant L for everything. And especially when we speak about global Lipschitz on the whole Rn, which is unbounded space and so on, then it's not easy to find Lipschitz functions, because these constant may grow with point, and it is difficult to find some biggest one. Before going further, what is meaning of this inequality? In fact, it means that the function is nonlinear. Sorry, this right-hand side f is nonlinear. Yeah, but this estimate says that basically we can estimate somehow with some very roughly with some linear behavior, because difference when you slightly change the state from x to x bar, then this function also slightly changes, but not only slightly, but changes in such a way that the difference is less than L times difference between these two states. So you can immediately understand that it is much stronger, or simply stronger property than just continuity. So before going further, we will often use the so-called Jacobian matrix of the right-hand side. So this is just notation. So we have this right-hand side, which is column vector of functions, and this column vector f is column vector, having component f1 up to fn. So Jacobian matrix we compute simply in such a way that this is matrix. By rows we change this component of f, and by row we change component of f, and by column we change the partial derivative. Yeah, this is partial derivative with respect to first component of the state, and this is partial derivative with respect to the last component of the state. So I'm sorry for 1 minute. I have here some question from department. Okay, so then of course one of the possibilities how to study Lipschitz property of this right-hand side f is that we consider this Jacobian, then we simply denote by L bar some constants for bounding each of these components, and also consider this norm of this matrix. And this notation will be used later. So why you need this notation? So we would like to have this very simple lemma called lemma lib, like Lipschitz, how to study Lipschitz property of F through these notations. So lemma says that assume that for every t from this time range we consider, this mapping from R to Rn is continuously differentiable with respect to x on some convex domain in Rn, and let for every fixed state from this domain this function again here from here should be Rn, sorry, in this second, from Rn to Rn, it should be not from R to R, I will correct it later, is piecewise continuous on J, where J is interval. Then we may claim that this is locally Lipschitz at every x0 from D. So let me say it more simply. The first property is first claim is very simple. It says that every continuously differentiable function or right-hand side is at least locally Lipschitz. So we can see that this is the main message you can remember to simplify this. Lipschitz is something stronger than continuity, but weaker than differentiability. So something in between the differentiability and continuity. So the first claim says that if you read carefully again all these assumptions, that basically we assume just that on some domain it is differentiable, and then we claim that this means that automatically it is immediately locally Lipschitz at every x0 from D. And now if we ask more stronger property that it is Lipschitz on D, that means then this constant L will be unique, then we claim or ask that all these constant here should exist in such a way that they bound these partial derivatives for all times t and all times x from these ranges, yeah. And then we, so if roughly saying, if every partial derivative is bounded by some constant, universally unique constant, for all x and t, then we will have Lipschitz property on D. And moreover, the respective global Lipschitz constant is less than this. We can have some estimate of this global Lipschitz constant. So here I drafted some simple proof. So first of all, now why we need convexity. So here I would say that we initially spoken only about connected open subset of D, which is called domain. So domain is connected, and connected, it's intuitively clear definition. It means that it doesn't split into two separate open sets, yeah, or every 2 points of connected set are connected by some continuous curve. Yeah, so I mean, this is notion which can have many subtle mathematical definitions, but intuitively it is very clear. Connected is simply something what is connected, and it's not split into separate pieces. And in this respect, you may remember definition of what is convex. Convex set is usually set where every 2 points can be connected by segment, by straight segment, and all these segment belongs to the set. So you really see that connected set in something a little bit weaker than convex set, because in connected set you may connect 2 points by some say curve which is continuous only, but in convex it should be straight line or straight segment. And why we need it? We need it here in the proof because we want to use Taylor's expansion. Yeah, and Taylor's expansions for vectors. So this, remember, these are vector functions. So you may remember that exactly we will here have this Jacobian. So difference between 2 points is equal to Jacobian times difference between these arguments. So this is simply Taylor formula, and we use this Taylor formula which says that the Jacobian should be evaluated somewhere in between x and x bar. Yeah? So you can see here is some unknown point between x and x bar. Tau is any constant from 0, 1. So this is standard Taylor expansions in vector calculus, which perhaps you met in first or second year in mathematics. So you can see here, for instance, that if theta is equal to 0, then we are in point x bar. If theta is equal to 1, then we are in the point x. Yeah. So as theta runs from 0 to 1, then this runs the segment connecting x and x bar. So now we just simply put here norms. So these are vectors, these are already 2 numbers. And of course, this equality should stay, yeah, because if two vectors are the same, the norm are the same. So this is nothing in this transfer unexpected. Then we may take quadrate here again. This should again hold when we just take quadrate, and then we may here see that this quadrate is this, and then we will use this inequality, and we conclude that this square is less than this. Here we use the well-known Cauchy-Bunyakovsky-Schwarz inequality, which you may also remember from some evaluations, but it is very useful also for many other areas. So I put it here. So it's like if you have n real numbers, a1 up to an, and n real numbers, b1 up to bn, and you consider this product, a1 times b1 plus a2, b2, and so on, then this product is less than as if you here take sum of squares and root and sum of squares and root, which of course, if you denote this like vectors, says that A transpose B is less than A times B. So this inequality, then if you apply it to this, then we'll give you some computations this, and you may conclude that actually L bar is the estimate for Lipschitz constant. So it is important to understand that L bar is just some conservative estimate for Lipschitz constant. Of course, in many particular examples, if you use some subtle computations, you perhaps may find that there can be even smaller L bar and so on, because you can see in this proof there are a lot of very conservative estimates and so on. But for our purpose, we would like to know that L is finite and the same for all x, so it's good enough. So this summarizes somehow or are some consequences of the previous lemma. So for instance, I'm speaking about this a little bit in detail because you will perhaps not today, but next time also consider some example in exercises. And also in Khalil book, if you look through these exercises, I think after this first chapter, or also in this appendix, you often have task prove that this right-hand side is global ellipsis, for instance. Of course, in some purely academic teaching examples, it's of course interesting question to show it, but for examples which are some practical models, you usually would expect that they are Lipschitz, because otherwise we will see later on the model wouldn't be good, and practical models should be usually good. So one first property here, which is good to remember, is that if right-hand side is differentiable with respect to x from some d bar, and d bar now is bounded convex set, not domain. Yeah, previously it was convex domain, so it was open set, and we didn't say which open set. It could be very big set, yeah. But here, if it is bounded convex set, then ftx is Lipschitz on D. Why? Because simply differentiable right-hand side is also, this means that it is continuously differentiable, so its partial derivatives are continuous function, and you may remember that continuous function on some bounded set, or better say on compact set, which is in case of Rn bounded and closed set. Yeah. So on compact set, any continuous function has finite minimum and finite maximum. Yeah. So automatically we have that that these assumption of lemma are satisfied. There should exist these constant because we are on finite set. So of course, what is much more interesting is to study Lipschitz property, global Lipschitz property on some unbounded sets, and preferably on the whole Rn, which will be seen later when we understand how crucial Lipschitz property is for the existence of solutions of this nonlinear differential equation. So of course, linear and constant mappings are globally Lipschitz. Yeah. This can be shown perhaps easily, and also the property that linear combination preserves global Lipschitz property. It's also not difficult to see this. So this lemma can be used only for continuously differentiable with respect to X mappings, but usually we will meet even non-differential mappings that may be Lipschitz even globally. So this lemma is not so powerful tool, and typical examples of non-differential by Lipschitz mapping are those containing saturations, absolute values, or other piecewise linear mapping. So typical example is, for instance, absolute value of X. So it's easy to see that it is a Lipschitz function, but of course at 0 absolute value is not differentiable. So this lemma is good only in some situation, but when you see that right-hand side is differentiable, then you can use this lemma to conclude Lipschitz property. And so in some examples or even in tests, you may meet this question: is this right-hand side Lipschitz or not? So another examples of very well Lipschitz functions are sinuses and cosinuses. So even on unbounded domains. And as I already told, this estimate of Lipschitz constant is too conservative, and there are few exercises in Khalil book. In this first chapter is written in really very simple way and with many examples, and there are some examples how to determine Lipschitz constant. And you will see that in these examples, if you apply this lemma, you will obtain, say, not so good Lipschitz constant as shown by Khalil in that book, which is nothing surprising. If you use here, we use just very general information about system. And if you have some particular system, then you certainly may always achieve something less conservative. So now I'm sorry that I have to little bit spend time about all these technical definitions about Lipschitz property, which might be a little bit discouraging because you didn't know clearly why it is needed. So now we came to the point why it is needed. And the very first basic lemma or property or claim is that if ftx is piecewise continuous and locally Lipschitz around some point x0 for all t from some time interval, t0, t1, then there exists delta greater than 0 such that this state equation, unforced state equation with initial condition xt0 equal to x0 has a unique solutions over this small time interval. So this is the same situation as a linear system. In general, this equation may have many solutions, and if we want to have one fixed, we usually should fix the so-called initial conditions. So at times t0, we ask that state is x0, and then of course we would like to have unique solution, existence of unique solution. But this lemma is very basic one. It asks the weakest requirements, just that is locally Lipschitz at x0. And then it guarantees only that we have unique solution over some very small time interval. So really, this is typical mathematical formulation. There exists delta greater than 0. And even no estimate how big delta can be. Of course, we would like to have delta as big as possible because delta is, let's say, some future horizon in time where we know something about system. Yeah? So if delta is small and we want to predict future, then we predict future only in a very short horizon. So it's almost useless, right? Unfortunately, this formulation can guarantee only this kind of typical mathematical claim that there exists some small delta, possibly small delta greater than 0. But the conditions are very simple. We just need to local Lipschitz property. So immediately there is some remark that this lemma is only sufficient conditions, and we will study it in exercises, maybe not today, but next one. Some examples that even if this right-hand side is not Lipschitz, then still solution may exist and be unique and so on. So it's important to understand that this is sufficient conditions. If we know that it is Lipschitz, then solution exists and is unique. If it is not Lipschitz, that we simply cannot say anything. So in many exercises or even homeworks or tests, there will be question, for instance, select the system which has unique solution and which doesn't have unique solution. Then it's really good to know that you use this lemma. If it is applicable, then you know that there is unique solution. If not, then usually you need a little bit more to do to prove that it is not, that there is not a unique solution or no solution. So here is a typical example which is repeated in all textbooks, that this equation with initial condition x0 has at least two solutions. So you can check it simply by substituting. So first solution is identically equal to 0 and second solution is this one. The advantage is that once you know some solution, you can simply check that it is solution very simply. Yeah. So this is problem of all solving equations. To check this something is solution or not is easy. You substitute and it is. But the question is how to solve when you don't know to solve, don't know solution. So here you can check this solution is really solution because identically equal to 0 function if you take cubic root. If you take cubic root, then you will have still identically equal to 0 function, right? And if you take time derivative of identically 0 function, it's again identically 0 function. So this is definitely solution. And here you can see that if you take this function and differentiate, so you use the well-known formula that it is 3/2 times 2t over 3 over 2 minus 1, and if you compute everything, that you will see that it is square root of this. Yeah, so just do it for yourself. Substitute here, take cubic root, substitute here, take derivative, and you will see that it is also solution. And you already can answer questions that this doesn't violate, does this violate this lemma LEUU? Not, it doesn't, because you can see that if you compute derivative with respect to x here, you will obtain x minus 2/3 in power minus 2/3, and the derivative doesn't exist at 0, and around 0 it goes to infinity when you approach to 0. Yeah, so you definitely cannot use, for instance, this lemma, because you are here interested in solution at x equal to 0, exactly at x equal to 0, derivative of this doesn't exist. So, but be careful, because we will show you later on some example where you can have also some cubic roots and so on, and still solution will be unique. Yeah, so this is just only, so this is not like that you say, okay, derivative doesn't exist, it automatically means that there are at least two solutions. No, it still may happen that there is only one solution, but this just explains that it is not contradiction with this lemma and that lemma, because really this function is not Lipschitz. So functions x cubic root at 0 is one of the most used examples of function which is continuous, but it is not Lipschitz. And here I put only for some completeness, it's good to remember, let's say for your general education, that there exists the so-called Peano theorem, which says that if f is continuous, then at least one solution exists. Yeah, so you may find perhaps is in this deeper Khalil book from early 2000s, some precise formulations or so on, but it's not necessary. It's good to know just this basic idea that continuous right-hand side guarantees at least one solution. But there may be several solutions. If you have Lipschitz property, then you have unique solution, but perhaps only on some small future interval. So just for your, say, acronyms, why I called it lemma LEU, I wanted to say that this is lemma on local existence in uniqueness, because in slides or in presentation, it doesn't make sense to create some numbers and then labels and so on with numbers and then quote it 5 slides later, because you see basically only one slide. So that's why I decided to use kind of these labels or acronyms rather than numbers. So why local? Okay, so now we came to another problem. So here you see that here, if you don't have even this local Lipschitz property, then you may have two solutions, but at least one solution exists. But but only locally. Locally with respect to future. Yeah, delta is like this future horizon. So now you can see example x dot equal minus x square. So this function is locally Lipschitz for all x from R. Yeah, so now we can apply this lemma and this equation, whatever initial condition you fix, there always exists unique solution on some time interval. Yeah. But now you can see here that it doesn't exist really for all time. So here really you will have some, this delta will be here some finite numbers. So you see that if you take this equation, take initial condition -1, then solution is this one, unique solution. But you can see that it is defined only on time interval 0, 1, and 1 is already cannot be included because this simply doesn't make sense for t equal to 1. So because here is 1 divided t minus 1, if it is 1, it is 1 divided by 0. Yeah. And so when this converges to 1, then this converges to infinity. So you may say exactly that lemma here works perfectly, but delta is equal to 1. T0 is equal to 0 and delta is equal to 1. So it's not bad because here even this lemma doesn't guarantee some particular delta. So 1 looks that it doesn't bad. It's not so short, but yet we would like to have solutions maybe on longer future horizon. This phenomenon is called finite time escape. So solution escapes to infinity in finite time. Here at time t equal to 1, solution in fact very strongly goes to infinity. So this is something different than, for instance, you may have unstable system with unstable linear system with pole equal to 1, so some exponential function e of t growing very rapidly, but yet even exponential growth, which is term these days understands perhaps every person, if every country, even those who don't know what is mathematics, now speaking about exponential growth, but still exponential growth reach infinity in infinity time. Yeah, but here we have even something stronger than exponential growth, something which grows to infinity as t goes to finite time, which is not good. So perhaps this kind of model is not reasonable for some practical systems, because usually we don't see that something grows in finite time to infinity. Now, what is the condition? How to avoid this is says by lemma GEU, the so-called global lemma on global existence and uniqueness. So now we simply ask that ftx is piecewise continuous in T and globally Lipschitz in X for all T from this time interval. Then the state and force equations with the initial conditions xt0 equal to x0 has unique solutions over t0, t1. So example is again linear system. If this time varying matrix will be bounded in some norm by some constant, then we may say that it has global solution. So global solution here means that it's all over this interval T0, T1. But if this T0, T1 now just is fixed because this dependence of the right-hand side is related to this global Lipschitz property that it should be valid for all T0 from T1. So for instance, if here there will be no dependence on time, then of course we may extend this interval up to the whole real axis. So there is another lemma which says that if this is piecewise continuous and locally Lipschitz on domain for all t from this interval, and we will have some compact, which means closed bounded subset, and x0 from V. And if we know that every solution of x dot with initial condition lies entirely in V, this property is usually referred that V is invariant, then there exists a unique solution that is defined for all t greater than T0. So this is a little bit better, because here we really ask that the function should be globally Lipschitz over whole Rn. And if we, in addition, we may have some function which is not globally Lipschitz, but from some other reasons, we know that solution cannot escape some bounded closed set, some compact set. Then it would be sufficient even local Lipschitz property on this domain D. Good example is again this one-dimensional system, x dot equal minus x cube. So if here is x dot equal for instance plus x cube, then you will see that this solution would escape in finite time to infinity. But if you put here minus sign, then again, if you compute derivative of right hand side, you will see that the system is not globally Lipschitz, because derivative would be 3x squared, and it goes to infinity when x goes to infinity. So on unbounded state space, it cannot be globally Lipschitz. But because of sign of minus here, we can conclude that any set cannot be left. So suppose that we have some set, some interval minus a with a greater than 0, and suppose we start initial condition in this interval, right? Then you may apply this lemma. Why? Because it's not difficult to see that if initial condition is from this interval, then solution also always stays in this interval, because minus x cube will have always opposite directions. So it's, if you start it in minus a, then derivative will be minus a cube, so it will be a cube. That means that at this point this is growing, yeah. And if you put here a, that is minus a cube, and it is decreasing. So all trajectories will come towards the origin. Yeah, system is actually asymptotically stable, which is notion we will study later in the future lectures, but intuitively you know, or from other courses, what means asymptotic stability. But definitely here, any of these intervals is invariant in the sense that if you start trajectory inside this interval, you stay inside this interval. And therefore, this is exactly what we have in this lemma. So we don't have Lipschitz, global Lipschitz property, but we have a compact invariant set, compact interval, and that means that we may conclude that solution exists for all times. And exactly as I told, if you take this solution, then you may try to compute solution, but this solution will escape very quickly to infinity in finite time. So again, the lesson or message is here that when you receive test question, tell me if this system has solution that can be extended on whole time interval or not, or it has finite time escape, then you cannot rely on this lemma. You can rely on this lemma only in such a way that you check that right-hand side is globally Lipschitz, and then you say, okay, this system has solution which exists for all times, always unique. Yeah, but if you check and you see that system is not globally Lipschitz, exactly as in this example, that you cannot simply give answer, okay, there will be finite time escape. Yeah? Again, finite time escape, you need to do a little bit more, some specific efforts to show that you have finite time escape. Okay, so now some remarks on proofs and terminology to conclude all these previous exposition. I hope you can read it quietly again at home, and you can also read this introductory chapter in this Khalil book, in this newer one. And so don't be discouraged that for the first time it's a little bit difficult to follow exposition, because when you have a bit more technical mathematical exposition, it is always not easy to follow it in the spoken lecture. You really have to read it again carefully, taking your time and so on. Okay, so terminologically, as I already told, solving ordinary differential equation with some initial condition is called initial value problem, but also Cauchy problem. Maybe you will meet this terminology. And any solution of Cauchy problem with some initial condition is called system trajectory. So when we speak about system trajectory, so there is any of solutions of these, and we may also then say that Cauchy problem is finding trajectory that crosses or goes through given initial condition. If you don't fix initial condition, then you may have infinity solutions of differential equation. You need to fix initial condition. And if system is good in the sense of these properties before, then you will have exactly this desired property that through every fixed state, there is just only solution, and exactly only solution which goes through this initial state. I decided not to spend time by proofs that can be found in many textbooks and so on. This lemma on local existence and uniqueness, earlier years I presented proof, and maybe it is in one of these Khalil books somewhere, definitely in this more detailed one, using fixed point theorem and contractic mappings, which is interesting technique, but needs a lot of mathematical introduction. Or good proof, I remember from my university when I was student, was just that you take Euler-like approximations of solutions, and then you prove that if you go with this step of Euler-like approximations to zero, then converge to something, and this is solution, and so on. So there are, I think that there is no time in our course to go in deeply in these mathematical proofs. And good observation is that the proof of Lemma-Leu usually concludes that this delta in this lemma formulation, this delta is kind of depends on many constants, but most importantly, it is proportional to 1 over L, where L is Lipschitz constant around any point. So if Lipschitz constant is globally bounded and system is globally Lipschitz, then what happens? That it happens that at around any point you may fix existence on time interval like this, and delta may be small, but bigger than some minimum value because L is constant. And then simply because for those, when you think about this lemma, one of the possibilities how to think, okay, I can overcome this short horizon in such a way that, okay, I take x0, I solve it on this time interval, right? I will have some solution. And then at the end of this interval, I will take this solution as a new initial condition, apply again this lemma, and again there is some delta that I can go a little bit further in the future and concatenate these many times. But problem is that if you have only local Lipschitzness, the delta as you move from point to point is shrinking more and more. But if you have global Lipschitz property, it cannot be shrinked, and then you know that, for instance, roughly saying, if you know that whatever initial condition you take, then delta is at least, for instance, 1 second, yeah. Then mounting 1 second many times, you can reach even years, yeah. But if you know that first step will be 1 second, then the second step will be half of seconds, and so on, then of course you cannot prolong to any future. Okay, so we still have a little bit time, and we may now start. So next, say next subtopic, which is concerned more specific dynamical systems, and that is even better, the so-called time invariant or autonomous unforced systems. So remember, up to now we were looking here at some dependence on time, but these systems may have even more, even better properties. So you perhaps know the terminology time invariant, yeah. But more interesting is that you may also met the term autonomous, which is interesting thing. Why? The fact that T is not present here is called autonomous when simply autonomous means something which is independent on external influence and so on. So one good example here is how to explain this terminology is that imagine that you will have some bigger system, split it into two parts, and then imagine that we actually look only on this X1 subsystem. So if X2 is not present here, then we would say it autonomous, because we can look at this X2 like on external influence on X1, yeah? So if X2 is not here, it is autonomous, yeah? And now if it is present here, so if we solve this equation, this will be some function of time, we will substitute it here, and we will see that it's actually dependent on time. So this is really interesting to think that behind this term autonomous, non-autonomous is the idea. So any time dependence around us is actually caused because we want to split some smaller part of reality. So roughly saying, if we will have differential equation describing all the space, yeah, all the space, everything what exists in the world, then this model should be time invariant, yeah. So this is just perhaps explanation why you can meet often autonomous systems, which means just that there is no present time on the right-hand side, yeah. And interesting property of autonomous system, which you will use, that if you have some solution, right, then if you take another time function, which is just solution shifted by some real constant, so this is solution, one function, and we will have another function when time is shifted by a, so xt minus a, then it is also solution, right? Why? Because this, if you differentiate this, then you differentiate this. This shift doesn't make nothing in differentiations, and you will see that this is equal to this, and this is equal to this. Yeah, and the only thing is that if you have some initial condition, that the initial condition is shifted in time. Yeah. So if this solution at 0 was crossing some x0, then this solution will be crossing x0 and at time minus a. Yeah. So that's why in autonomous systems we often say that we know more, that without any loss of generality, T0 will be always taken as 0. Yeah. Which again really also make the sense, because if we know that our system, for instance, we want to control or study some device, yeah. If we know that this device is all the time the same, that it's not necessary to take time in years, but you simply can take time from this moment now and consider this moment now as zero. And if you start to do something with this device tomorrow, then you again reset the time to 0 and start from 0, right? But if coefficients of the systems are getting worse or something is getting wrong with the system or it depends on time, then of course you cannot do it, and then you should always remember what is DC0. Okay, so thank you very much for today, and there are 2 minutes. Maybe you can say some short questions or comments or suggestions for future, but also feel free to write me emails, and I can answer emails and so on. Okay, so thank you. That's it.
Thank you.